Do we happen to have a laser pointer? Oh, okay. Yeah. Okay. Thank you, Sarah. Okay. Good afternoon, everyone in the room and online. I am standing between you and the happy hour, so I will try to be quick. Okay. I am from UC Berkeley, which is located in the Bay Area. As you know, that is a very cool area. Last night, I came out of the Las Vegas airport, walking into the heat wave. That makes me really feel, how valuable kind of research we're doing here. Okay. I also normally give a presentation and interact mostly with academia. I gave presentation in MRS, APS. Very rarely I interact with this community, and thank you CRRC for giving me this opportunity to network and to interact with some of you. In fact, I have already been discussing with some of you on collaboration. So I am, okay. How do I, the arrow or the return? Okay. Oh, okay. Okay, so I'm going to first introduce thermal radiation. I guess for this community, I don't have to do that, but for completion purpose, I'm going to do that anyway. So I'm going to talk about how we engineer thermal emissivity with phase-changing material. And then I will introduce, based on that, in my group, we recently developed 3 new technologies. The last one is the one that you will be interested in. But again, because the first 2 are also related in terms of the physics and the mechanism, I'm going to talk about that. So anyway, so heat, conduction, and radiation. As we know that both are very important, including the convection, are all very important for managing the temperature of a building. But here, let's talk about the thermal radiation. And again, this slide is coming from one of the classes I'm teaching, that when I talk to students, they got confused. What is a thermal radiation? It's basically the Stern-Boltzmann law, right? People talk about black body radiation, but not everything is a black body. So for a gray body, you scale the black body radiation power by this constant, we call that emissivity or emittance. And so this emissivity is a temperature independent parameter for most materials. As you see from the bottom here, that graphite is constantly high, copper metal is constantly low, semiconductor like silicon is constantly in the middle. So just because the emissivity itself is constantly independent, then we can claim the Stern-Boltzmann law, which says the thermal radiated power is proportional to the T to the 4th power, because the epsilon here is a constant, okay? But what we did in my lab is to break that law. We engineer a material, phase-changing material, I will show you in the next slide, that the thermal emissivity is no longer a constant, it's dependent on temperature. In fact, the temperature dependence of emissivity, we can almost arbitrarily engineer that function. We can make it increasing as a function of temperature or decreasing as a function of temperature. So how do we do that? We do that using this phase-changing material. Now, when we talk about phase-changing material, people think about molten salt. Some other people think about GST for the the optical disc material. But here I'm talking about vanadium dioxide. So the material is a magic material. We have been working on that for many years because the material automatically go from one phase to another phase. All you need to do is to change the temperature. You don't need to put in electricity or laser pulse or anything. Just increase the temperature, you will go from insulating phase to a metal phase. It is going to go from a very, very electrically insulating material into a very, very highly electrically conducting material. Okay. The mechanism has been still debating for decades, is still in debating by the physicists. But now let's look at how we can make use out of the material. What I show you here is the material we synthesized in our lab, in which vertical is a sigma is the electrical conductivity, horizontal is temperature. Now, when you see a big jump, that means the material goes from insulating phase at low temperature to a conductive phase at high temperature. The black data points here, that is the pure vanadium dioxide. The phase change temperature is 67 degrees C, okay? It's 341 Kelvin. How many Fahrenheit? You can calculate. But that is way above room temperature, not useful for roof coating. But we can reduce that temperature by simply putting a little bit of tungsten in it, like 1.5% of tungsten, replacing vanadium. You can then reduce the phase change temperature to exactly at room temperature, okay? Not only that, you can also make what we call gradient doped vanadium dioxide. If you just dope it uniformly, you shift the phase change temperature, but the phase transition is still very abrupt. Now, if you grade dope it, then you can broaden the phase change from a very narrow temperature range into a very broad temperature range. And that is then very good for you to capture whatever interesting temperature range you want. So how do we grade dope it? It's basically you grow multi-layer. Each layer is very thin, has a specific doping concentration. Then you post-growth anneal it. The annealing will drive the tungsten to diffuse. You end up with a film. The surface is heavily doped. The bottom is undoped. So that's what we call gradient doped. Okay. Now, as I mentioned earlier, that most other material, the emissivity is a constant. But for vanadium dioxide, because of the phase transition, the insulating phase has a high emissivity. The metal phase has a low emissivity. It's understandable because metal typically they have a low emissivity because electrons can reflect, the thermal infrared radiation. So the vanadium dioxide is going to have this abrupt step function dependence on temperature. That is not what I want. But fortunately, as I said, I can dope vanadium dioxide and I can grade dope it. Depending on how you grade the doping profile, you can then design and realize an arbitrary temperature dependence of the emissivity. Okay. So here I just draw you randomly 3 different curves. So one example, the first example is the Stefan-Boltzmann law says P radiated power is to temperature to the 4th power. What if I engineer epsilon to be T to the -4 power? T to the -4 times T to the 4th give us a temperature independent thermal radiation. Okay. And what is good about that? We all know that for thermal camera, the camera detects the radiated power, but the camera does that remotely. The camera does not really know the surface emissivity of the object. The camera would assume that the emissivity of your surface is 0.9 or 0.85, and then convert the radiated power received into the TIR, the infrared temperature. That's how your thermal camera can tell you the surface temperature. Okay, but this TIR obviously is different than T, the real temperature T. If you take the derivative, you find that dT IR over dT is equal to the equation on the bottom. Now, for normal material, because epsilon is temperature independent, then this TIR and the T, they are linear. They go linear, which is fine. That's why night vision goggle, your thermal camera work. But now in our case, we can engineer epsilon to have a temperature dependence that is a positive negative, small, big. That gave us the opportunity to completely, change this T dependence of TIR. Okay. So for example, I'm supposed to have, yes. For example, here it shows you our experimental data in which here this is the emissivity, that is a T to the -4 power dependence. And we designed that and make that happen. It's not accidentally, find that sample. We designed that to be T to the -4 power. Then times T to the 4th power give us the thermal radiation, which is a constant, as you see from the bottom. Now that T-independent thermal emission can be used for thermal camouflage. So on the bottom here, this 4 figures shows you that if you use a thermal camera to look at our sample, you find that the temperature, the visual thermal temperature is a constant, regardless of whether the environmental temperature has changed. So that's the thermal camouflage. Not only that, we also engineer an advanced version of the thermal camouflage. We call that a decoy. So what is a decoy? The camouflage basically hides the temperature, while decoy actively cheat the camera by designing the thermal pattern that you want. So here I show CAL, and some of you know that Cal is a nickname of UC Berkeley. CAL here, C is made of a multi-layer of vanadium dioxide, in which we engineer the thermal temperature to be 5 degrees, and A to be 15 degrees, and L to be 25 degrees, regardless of the real temperature. If the real temperature increase or decrease, C is always 5 degrees, right? A is always 15 degrees, and L is always 25 degrees. So that's what we call a decoy. And you can make any complicated pattern with any thermal temperature picture that you want. So that's what we call a decoy. Okay. So now let me move on to my second technology that we invented. The first one I already showed you, is a thermal camouflage. The second one has to do with the fact that can we switch the thermal emissivity oppositely? Because previously in the thermal camouflage, the emissivity is going downward, right? High temperature, you have a low emissivity. How do we switch the opposite way? And I will show you why we want to do that. But can we do that? Yes, we can do that, but you have to do something extra. The way we achieve that is to make a triple layer structure. Here, the top layer is a tungsten doped vanadium dioxide. It's a periodic structure. It has a fancy name. It's called meta surface. Now, the middle layer is a dielectric layer that is transparent to the thermal infrared. The bottom layer is a metal reflector, it's silver. Now, when temperature is low, the tungsten vanadium dioxide itself is a transparent dielectric. Then the infrared light comes in, will be reflected completely. So the reflectivity is 100%. Absorption is 0. So therefore, the emissivity is also very, very low for the low temperature case. Now, when temperature goes to the above the phase change temperature, the tungsten vanadium dioxide become a metal. Now, what you have now is a cavity, is a resonance cavity between the top layer metal and the bottom layer metal. And that resonance would allow you to have very strong absorption of the thermal infrared light only at high temperature, right? Because only at high temperature you have a cavity. We tune the structure, the thickness of the barium fluoride to make it to be in resonance with 10 micron, because 10 micron is the middle of the sky window spectrum. And here I show you our simulation versus experiments, and clearly you see that the emissivity and also absorption they strongly depend on temperature, and they switch to the other way. Okay, so that is the mechanism. So the first application that we use is to make this as what I call that TIS, thermal imaging sensitizer. So we made the sample into a very flexible tape, like as you show here, as you see here, a tape that you can peel off and tape back on and peel off. You can use it repeatedly on any surface you want. But once you cover your surface with this TIS, you can then amplify the surface temperature into a large temperature. So how do we do that? Because the thermal camera detects the infrared temperature, TIR, vertical axis, versus horizontal axis is the T real temperature. We'll have a very rapid increase at the phase transition. Now, if you have a small delta T in the horizontal axis, you're going to have a large delta TIR in the vertical axis if the temperature is tuned to this high slope, right? So in that way, you can amplify small t on the surface into a large delta TIR by the infrared camera. So we did the experiment here. We put two very small heaters next to each other, millimeter away from each other, using the regular thermal camera that $100 that you can buy from the market, plug into your cell phone, you can then take an image. You won't be able to resolve those two hot spots because they're so close to each other, your camera does not have a resolution. But now if you cover the surface with TIS, you can clearly see that I have two bright spots, right? Because now I can then amplify the surface delta T of millikelvin into tens of millikelvin. Then using the same camera, you can resolve the temperature. So that's why I call that thermal imaging sensitizer. The amplification ratio is about 15, from 3 millikelvin to 45 millikelvin. So by doing that, we can have a millikelvin resolved thermography at room temperature without using the cooled bolometer. This is everything is room temperature. There are many applications here, including microelectronics, healthcare, and the construction business. But let me only show you one example. The example has to do with the biomedical imaging. And we did experiment with a biology professor on the campus, and we inject tumor cells into the skin of the mouse. All right. And then we monitor the tumor cell growth on the mouse. So as you see here, day 3, you use optical imaging, or you use infrared imaging without my TIS, or you do the infrared imaging with my TIS covering the skin of the mouse. You see that only for the infrared imaging with my TIS, you can see two very small but clear cold spots at the place that you inject a tumor cell. Okay, so at the day 5, you can see that two cold spots grow bigger and bigger. And day 7, you can see that cold spots corresponding to the tumor. You use other technique like the regular thermal imaging, you can also see the cold spots. I was told, I'm another biologist, I was told that the tumor cell here specifically they can block the blood circulation, make those tumor plates to be slightly colder than the normal tissue. So what we achieve here basically is a thermographic detection of subskin tumors at an early stage, at the stage that is that you won't be able to detect it using a regular thermography. And we are thinking about this could apply not only for mouse, but also for human being, like breast cancer, right below the surface of the skin, right? Now, let me now move on to my last story, which is the story that this community is most interested in, is the temperature adaptive radiative coating. And we have heard enough today about you need to worry about not only surface solar spectrum reflection, you also have to worry about thermal emission. Those two spectrum range, they are well separated, okay? That give us the opportunity to engineer them separately. But there is a problem here, because let's say I have to, for cool surface, cool roof, I need a material that has a very small solar absorbance, very high thermal emissivity. So I want my material to be sitting in this blue spot. But suppose you want a warm roof. Why do you want a warm roof? Because, in place like Las Vegas, probably you don't. But in other place like New York, all right, Boston, other place, even San Francisco, you need a warm roof in the winter. Otherwise, your overcooling problem is going to cost you more energy in the winter, okay? Now, one solution is, okay, every year I'm going to have a ladder, go up and switch my roof back and forth. That's not a good solution. The good solution is you find one material that can automatically switch between the cooling roof mode and the warm roof mode. And that is our invention. We call that temperature adaptive radiative coating that can automatically sense the temperature and do the switch without you to intervene. You don't have to turn the switch on or off. You don't have to put in the electricity. How do we do that? I will show you next page. But here, this schematic shows you how it works. In fact, the data points, those are our experimental data points, okay? We experimentally measured, we found that the emissivity, when temperature is below 22 degrees, emissivity is 0.2. When temperature is above 27 degrees C, the emissivity is 0.9. So there is a big switch here, okay? The mechanism is almost exactly the same as what I show you in the thermal imaging sensitizer case, right? You have a multi-layer structure, right? The phase transition from insulating phase to metal phase allow this thermal, the resonance at a 10 micron wavelength range, okay? So here, what I show you here is the real experimental data in which, as you see here, that when you go from low temperature to high temperature, here, the emittance, if you integrate, you get the integrated emissivity change from low to high, okay? So that is experimentally measured spectrally resolved emittance. And this conclusion is adapted from our publication. A smart radiative coating automatically switches thermal radiation power in response to ambient temperature via a metaphotonically amplified metal insulated phase transition. And we have done simulation showing that it outperformed all existing roof coating for most of the climates. I will show you the details. So first, let me show you that we have done vacuum experiment to exactly measure the cooling power. And we found that, look at this cooling power plot, switch from a low cooling power, about 20 watt per meter square, to a high cooling power at a high temperature, about 110 watt per meter square. We have also done outdoor measurement. In fact, my student did that on the roof of my house on the Berkeley Hill, and where you can see the Golden Gate Bridge. The reason is because on the Berkeley campus in the pandemic, we could not really find a roof access, right? The building are all locked down. I said, then come to my roof. I have a nice roof over there. So he set up all the electronics, Wi-Fi connection on my roof, and my 9-year-old son was very excited to be the research assistant to my student. So we have done multi-days of data recording, and just basically the summary is that our TARC, temperature adaptive coating, surface is cooler than the reference in the daytime, is warmer than the reference in the midnight. As you know that in midnight in the Bay Area, especially on the Berkeley Hill, can get really, really cold, like 10 degrees or below Celsius, even this month, okay? So let's come to the simulation. And here, Ronan has helped us a lot because I'm not in this, field. I'm a material scientist. we learned a lot from Ronan, in which we did the simulation very thoroughly. We include, short wavelength light absorption, long wavelength radiation, and also wind convection. And then we simulate how our TARC roof would perform in comparison to other non-switching roofs. So on the bottom here, this is the city of Berkeley weather database. So here, from January to December, and from 0 hour to 24 hours of the day. Obviously, you're not surprised. Midday, from June to August, you have a hot spot. Temperature is really hot. So we designed our TARC to have a switch specifically capturing that hot spot. Our emissivity is low everywhere else, but it is really high when the temperature goes above this 27 degrees C, okay? So then we calculate how much, surface temperature can lead to the energy saving. On the right-hand side is the minimum energy saving of this switchable roof compared to other roof material. So other roof material, as long as it is non-switchable, we give it a fixed solar absorption. That's the horizontal axis here. A ref, and then epsilon ref. Any other arbitrary non-switchable roof material for city of Berkeley, they always consume more energy than my TARC material, which is understandable because Berkeley is the place that when it is hot, it's really hot. When it is cold, it gets really cold, okay? Now, one thing I have to emphasize here, we have heard from Jonathan about the importance of albedo. But there is a caveat here. If you talk to the cool roof research lab, what they target on is to reduce the solar absorption as much as possible. Ideally, zero absorption, 100% reflection would be ideal for them, right? But by simulation, we found that that is not the case. In fact, if you tune the solar absorbance to be somewhere in the middle, like 0.25, 0.3, you can achieve more energy saving all year round from winter to summer. That is because if you, in the winter, you do need a little bit of solar absorption to warm up your house, okay? The optimum solar absorption is not zero. It's neither 90%, is in fact location dependent. As we show here, for example, San Francisco, for example, that's 3C. Then the optimum solar absorbance is about 30%. Okay. And we have designed our TARC material to specifically have this non-zero, non-100% solar absorbance. So the material would look like not really shiny bright, also not black. It is like a grayish color. Putting everything back into the simulation code, we have calculated how much energy we save by using TARC versus using any other non-switchable roof material. And what you see here, if the circles, right, with a different color and different size, the blue circle means that we are worse. The red circles means that we are better. Now, we are worse in Miami, in Phoenix, because those places are constantly hot. You will just use a cool roof, you will do better than my switchable roof. In other places like Alaska, I don't know which city that is, it's constantly cold. You just need one single warm roof material, you will do the best. But for most other climates in which you have a seasonal variation of temperature, the switchable roof can save more energy. Okay, the size of the circle tells you how much energy you are saving. Right, the bigger the circle, the more energy you can save. Right, so one last comment here is that we can use this technology not only for roof coating but also for many other applications, vehicles, electronics, I was talking, over lunch about going out for camping. You feel really cold in the tent, in the middle of night, right? In the midnight. But in the daytime in California, right, when you have sunshine, it feels really, really hot. So putting that on the tent would also solve a lot of problem. Now, specifically, I want to emphasize this. I was approached by some folks in the defense industry, and they want to use this for a space object. As you know that if you have a satellite or space telescope, if the surface is facing the sun, the surface will get really, really hot. If the surface is facing away from the sun, it will get really, really cold because there's no atmosphere, right, to neutralize the temperature. So in fact, our simulation here shows you that temperature can go from minus 150 to plus 150 degrees C. And that large variation of temperature can be very detrimental to the electronics and the battery and solar cell of your space object. And we also simulated that coating the surface with our TARC, we can essentially cut down the temperature swing to make it to be almost flat, constant, at the comfortable 25 degrees C, okay? So that's one application, and we are working on the experiment. There are a few other future opportunities. So for example, we are working with some research groups to make the TARC. Right now is a solid membrane. We make that into a liquid paint. And I invented this funny name, TARP, T-A-R-P, temperature adaptive radiative paint. And we also can think about not only radiation adaptive, but also solar absorption adaptiveness using the phase changing material. We can also even think about convection adaptiveness, okay? How do we do that? Solar adaptiveness can be achieved with thermochromic material, and that has been already there, but just nobody used that for this purpose, right? Convection adaptiveness, you know that the surface convection of air really depends on the surface morphology. And this is from our experimental data that using the phase changing material, you can really change the surface morphology, adaptive to the surface temperature. We have not, we did this experiment for optical studies. We have not got a chance to study the convection effect, but I think it will have an effect to the convection heat dissipation. So with that, let me acknowledge my collaborators, very importantly, including Ronan here, my group members, my funding from DOE, NSF, and from my Baker Foundation. Thank you very much.